So we're going to move on and build on that. Our second speaker is from ZIN Technologies. His name is Christopher Sheehan. If you're looking for his bio in your program, you don't have one. And the reason you don't have one is because Murphy is always around. What can go wrong will. One of our three speakers bailed out the day before we started the program. So we had to scramble, and Chris was kind enough to jump in. So we are excited to have you talk about ZIN Technologies. If you want to introduce yourself a little bit. Okay, thanks.
Thank you, Ven. Thank you, OAI, for having me here today. It's an honor. I'm the Vice President of Engineering for ZIN Technologies. We do spaceflight hardware for NASA, so mostly ISS payloads. In fact, ZIN has put up 75% of all the physical science payloads since its inception. So we work very closely with Glenn Research and other NASA entities to do that work. We recently were acquired by Voyager Space. I've been at ZIN for 20 years, so I've been an engineer, I've been a project manager, and so I've begun to lose my grip on any kind of technical knowledge. But I do have a mechanical engineering degree and a master's in physics, so I try to at least stay abreast of what's going on. I sort of maybe haphazardly titled this Bio-Inspired Solutions for Human Spaceflight. I really don't work with a lot of biomimicry, bio-inspired type approaches to solving problems. I come from an industry that's very conservative. I came from commercial aerospace before I started at ZIN, so I'll talk about some of the challenges in actually doing these types of things that we're talking about at this conference. I'm going to give you a little bit of a background on ZIN. Okay, ZIN's been around since 1957 in various incarnations. They've supported Glenn when it was Lewis Field. Most everything you see on this chart here, up to about 2013, we really were just doing work with NASA, shuttle payloads, Mir payloads, the International Space Station, sounding rockets, those types of things. Around 2013, we started doing more commercial space work. We did our first payload for the Goddard, NASA Goddard, for the magnetospheric multi-scale mission. Is basically 4 satellites that are still flying today that are mapping the magnetosphere. And you talk about guidance and control to keep things flying in formation. I think you can start to see some parallels to nature, okay? That by the way, was not planned, but you can start to think of these things in terms of nature, how control algorithms work with starlings flying in formation and satellites flying in formation. There are strong sort of analogies between the two. We've done multiple electrical propulsion systems with NASA Glenn and Aerojet Rocketdyne, and you can kind of see down at the bottom, we're now working on a commercial space station that is going to replace the International Space Station by the end of the decade. And so Voyager is a company that has multiple entities under it. We are one of them. The other sister companies all bring something to the table for low Earth orbit commercial space. So you just saw the temporal timeline. This is the spatial. I'm going to point out, we do work at JPL. We do work really all over the country, and you can see some of these projects up here. We even have some work with JAXA in Japan. They're actually coming in at the beginning of November. We're doing a guidance and nav system for some of their satellites. And commercial space has sort of been something that's been picking up over the last 3, 4, 5 years. We have dealt with an unprecedented number of requests from companies like Blue Origin, and folks that are looking to get to not just low Earth orbit, but to get to the moon. So there's all kinds of activity we have, and this just kind of gives you an idea of what we've been doing for the last 20, 25 years. So we power large missions. These are some of the highlights of things that we've done. So in addition to the International Space Station, I don't know if any of you saw in September when NASA slammed into an asteroid and changed the orbital period of it. We had a power system on there that powered the gridded ion thruster. That was not the primary propulsion system. They had demonstrated it earlier in the mission, and if they missed, they were turning around with the ion engine. So that was, we're glad that they fulfilled their mission, but we were also, interested to see if we could actually answer the bell if they missed for some reason. Sierra Nevada's Dream Chaser. So this is a resupply America's space plane, as it is called. This is functionally a reusable platform to get cargo and possibly eventually crew back and forth from the International Space Station. This will be at Armstrong Test Facility, I think, in the next several weeks. The bird is getting Vibe and TVAC tested out there. Lunar Gateway, we're doing another space station out by the moon, NASA is. We have some small subsystems that we're working on that, including structural health monitoring, something that in situ will be able to characterize the vibro-acoustic environment and the fatigue life of the structure. So it's a pretty sophisticated sensor that will allow them to understand really, second by second, what loads are getting imparted into the station. OSAM-1, this is just another spin of the thing we did for MMS, and we do some acoustics analysis for the upper stage for launch vehicles. So here's Starlab. This is just an artist's rendition, obviously. This is what we are working on in concert with Airbus. Ohio State University, OAI is involved. This is really kind of a big deal for Ohio. The ground mock-up of this spacecraft, of the space station, will be at The Ohio State University. It'll be down by Don Scott. So researchers will be able to come in and actually have an exact replica of what is going to be, hopefully by the end of the decade, floating around up there. Of course, doesn't have the zero gravity or the radiation environment, but all the other environments will be simulated, and they'll be able to interface their hardware before they actually send this down to a launch facility to get their payloads launched. So we're very excited about this. This is a privately financed thing. The guy who owns Voyager is like an Elon Musk light. I mean, he's only worth a couple billion, and so he's putting a lot of skin in the game. And Airbus is our European partner. They're going to be doing the spacecraft. So ZIN will be doing a lot of the payload development, the rack interfaces, a lot of things that we did for our ISS development over the last 20 years. So shifting gears, so that's ZIN, and again, I come from an area of development that really doesn't take biomimicry and these types of sustainable things that you've been talking about for the last couple of days into consideration. However, in doing some research for this, I noticed that really the number of publications is sort of in the aerospace world, now, not just everywhere, just in aerospace, it's starting to get traction. You can see that this is starting to pick up. Leveraging natural structures, self-assembly, all the things that maybe you've heard in the last day or so here, these are really getting traction in the aerospace world. And I was happy to hear that the systems folks are starting to adopt this, because really systems engineering is sort of the heart of the project, right? There's a project manager, and there's a bunch of engineers that have their little silos, and the systems person kind of pulls them all together. So that's really great to see that's actually starting to get into the literature and sort of the standards. So issues in the space environment. By far and large, the hardest thing to do is not to launch a space vehicle, it's not to land a space vehicle, it's protecting and sustaining a human being. Okay. If we just sent probes out, for the next 20 or 30 years, we would have a very high success rate, and I don't think we would learn nearly as much as by sending human beings, okay? So you think of some of the things that are issues in the space environment. Thermal management. You look at the spacesuits back in Apollo, these are the huge clunky things, but they had to do a lot of things. They obviously had to protect the astronauts structurally. They had to be thermally controlled. Maneuverability is just, is a huge thing. If you're talking about sending humans back to the moon and having them do EVAs and all these types of things, and they can't just be hopping in this sort of clunky suit. Fatigue is a big problem, and the musculoskeletal health, right? So what sort of things, in nature can we do in the spacesuit and other things to sort of help these situations, which I'll talk about in a moment. Just randomly selecting an environment, because all space environments are harsh, but if you look at a lunar environment, a lunar dust gets everywhere, right? So what solutions in nature are there to prevent dust from permeating? And if you look at the literature, there's actually some interesting coding ideas based on various natural phenomena. Structures, how do you build them? How do you get them there? I mean, you can't launch something that's fully assembled, right? You need something like deployable structures. You need to look to nature to find out how can you efficiently do this. I mean, every pound that you launch is, tens of thousands of dollars. So you've got to minimize that. It's really a big area of focus. Thermal management again, and energy collection and storage. All of these things have sort of natural analogs that are being explored, and it's really interesting to look in the literature and see how over really just the last 10 years, NASA in particular has started to look at some of these items. I found some things, that kind of answer some of the questions from the last slide. If you look at the Z2 prototype suit, this is about a 7 or 8 year old concept. You're drawing things from the oceans, okay? You're using bioluminescent qualities in the suit, scaly skin of fish to help with the type of structures that you need, but also the flexibility. This was an interesting, this is a NASA project. So this is 7 or 8 years old. There was an open spacesuit challenge. This is kind of separate but related. How do you, in zero gravity, keep your muscles from, atrophying and your bone density? When we're on Earth, we have our body weight, we walk around, and we're generally okay. When you're not loaded and when you have this fluid shift, when you're in microgravity, you start to lose bone. You start to lose that muscle health. Well, a lot of these challenges, people came back and said, well, we'll build this giant, type of exercise device. It'll be, springs or spring mass damper, some type of thing. And there was an interesting sort of entry, and this is about 4 or 5 years old, that was using the exoskeleton of insects to adjust sort of these strain loads, okay? So maybe you're not getting the bone loading there, but that people are starting to think about things in terms of, okay, how does nature protect? What can we use and leverage for these unique environments that, no one knows what it's like if you live 10 years in microgravity, right? The longest resident of the International Space Station, I think, is maybe a year. What if you have whole civilizations that evolve, if you have children on Mars, for example, in a 3/8 gravity environment? These are things we don't know. These are things that we need to find solutions for. Deployable structures, and this is an MIT sort of thing here. They're looking at sort of deploying these structures on the moon and looking towards really worms, segmentation, composite inflatable solutions that use the segmentation of worms. You can launch these things compact, they sort of expand, you reinforce them. There's a wonderful article that I pulled some of this information from MIT, that you have people working this issue here, and there's all kinds of wonderful solutions. Again, people are looking to nature to try to solve these types of situations. And separate but related, another MIT group is doing this sort of wonderful, they call it semi-aware self-assembly, okay? You launch these little tiles, okay, and there's sort of these assemble in these geodesic type of domes, and you can really build blocks. This is analogous to sort of self-assembly you see in colloids in nature on the small scale. So there's wonderful things that people are doing. This project's actually funded to do multiple parabolic flights. They're going to test this in zero gravity. They're going to take this type of thing and develop it. So that's really great to see. Quickly here, before I get to the last couple slides, I really want to spend some time on. You look at the pomelo peel here. Instead of evolving into just a super hard skin where if it fell, it would be protected, it actually has a sort of a foam layer. Okay, it's like a shock damper. And all the things that you launch into orbit, sensitive instrumentation, requires vibration and shock isolation. There's all types of smart structures that you could possibly do in lieu of just, spring mass damper type things. So I thought this was an interesting article also. So quickly, challenges, and I alluded to this at the beginning. The aerospace industry really drives, up to this point, I will say up to the last maybe 10 years, has really driven the flight system development. This is a conservative industry, right? If we never want to reinvent the wheel, we really don't want to invent anything. We want to buy subsystems and make things go with as little what's called non-recurring engineering, which means, engineers have to get in a room and figure a problem out. It's a conservative industry, so adopting these sort of bio solutions is going to be tough, right? Timelines are getting shorter. There's a race to commercialize space comm and imaging and all these satellites in low Earth orbit, and they don't have time to really spend on new ideas. It's entrenchment, really. I have a quote here from Feynman. He says, "I noticed that when I was younger, a lot of the old men in the field couldn't understand new ideas very well." And he's talking about string theory here. He was a QED, QCD guy, and he's an old man now, and these new ideas, they look crazy to me. So this is the type of thing that you're going to be up against if you're trying to adopt these types of changes, these sea changes in the aerospace industry. And I'm part of the problem, right? I'm a 50-year-old man who's who wants to solve problems. I've got limited budgets, schedules. So there will be challenges, I think, for as much promise there is out there. What we can do, and again, I'm a kind of a neophyte to all of the biomimicry, so I'm not speaking from a point of authority, but there's a way to make this a tool in the toolbox for engineers, right? There's a way that, Venn can teach classes, students can find unprecedented information online and literally make this a tool in the toolbox. It's part of the decision and the development process in the systems V. You can get your requirements, and before you go into this sort of ideation and this product creation, you have an opportunity to do a trade study where you're considering various bio solutions. I think that's possible. We need to continue to outreach and teach these concepts, These types of classes, when I went to school, I really would not know if they existed. They certainly weren't well advertised. But yeah, so we're just to sum up here, we're at a point in, I guess, history where young people have an unprecedented access to information. Velocity of it, the volume might be staggering, but there's tools out there that you can use. We're also at a point in history where we've never been asked to discriminate and filter information stronger. There's so much of it out there. You have to be the arbiter. You have to decide, what is useful to you. And so I think that's it. Thanks, guys.